Hi everyone, and welcome to chapter 2 about the spanning tree protocol. I like this chapter so much I'm going to divide it into 3 parts. First, just a general introduction to spanning tree, 10 slides or so, then into a little bit more complex bit on the implementations of spanning tree, and then some alternatives in the third part. But I think spanning tree is such an important concept that really will take even if we take 2 weeks to get spanning tree down, it's going to be worth the effort. So let me hide my camera, and then we'll get on to talking about what's in here. So spanning tree concepts and spanning tree configuration. We'll get into that, the configuration part, a little bit later. But first, I want to talk about redundancy, the idea of redundancy at layer 2. Redundancy we've talked about when we're planning networks, and it's represented in the graphics in the previous chapter by multiple cables between devices. And we all know that redundancy improves the reliability of a network, just because having 2 of something handy is always going to work better than having 1. But it's expensive. But there's a special problem when you start working at layer 2, because the frame structure at layer 2 is different than layer 3. There's no TCP/IP, there's no correcting, there's no mechanisms. It's a very simple frame format. And so when it starts pushing out at layer 2, if you add redundancy, some special problems happen. The MAC addresses get, as you may recall, MAC addresses are flooded out every port on a switch. Because there's no way to know to populate the address table, etc. So a device comes through a switch, populates out all devices. Well, that if we have redundant switches, that would include sending it to the other switch. And if we do that, then that switch will populate as well, and it will loop around, as we'll see in a couple of the graphics here, causing what we call a broadcast storm. Now, if you could see my face right now, it would be bright red, because I must tell you, I once took a network down with spanning tree, so it's a topic near and dear to my heart. I know firsthand that it takes but a microsecond or two to take an entire school down if somebody plugs in a non-spanning tree switch into a spanning tree network. You might ask me how that turned out, but I'll save that for another time. So the things that we're wanting to take care of, or the things that we're wanting to watch for, are the MAC address instability, the broadcast storms, kind of the same thing, and multiple frame transmission. Those are the things that cause us to run into trouble. So Ethernet frames, they don't have a time to live attribute. That's the main thing. Remember the TTL, we use that in traceroute, and that at layer 3. Layer 3 has the time to live built in. Layer 2 does not. And because there is no time to live, it keeps going forever and ever. And it's that endless circulating, and every time it floats through 2 switches, adding another frame, that's what causes the storm to be fatal. So they're constantly updating each other when they're caught in a loop. This is a lot of text here. Let me move on to a possible diagram. So what's going to happen here is that PC1 will send something into the switch, right? And then the switch is going to plug that MAC address for PC1 out to these 2 switches, which is great, because now they have it. They have the MAC address in their table, except that because they're receiving it as an update, now they're going to send it out this way, all right? And switch 3 is going to send it out this way. And then pretty soon that's going to come around and come back this way, and the joy will go round and round for a second, or less than a second probably, until the switches become so overrun with MAC address updates that it can't run. Okay, that's the main reason that the spanning tree was created. The spanning tree protocol runs on switches, created by the great Rita Perelman. I highly encourage you to go to YouTube and look her up. There are even people with songs and odes to her. She developed this a long time ago, and she's one of the rock stars in the IT world because of it. So go ahead and check her out. Rita Perelman. So she wrote this, and what she decided was, and if you look on Wikipedia for an example of a spanning tree algorithm, you'll see why I'm not getting into it here. It's well beyond the scope of this class, mathematically. But what it does is, on all the redundant links, that is links with two cables, essentially spanning tree chooses one and puts it in an inactive state until it's required. So the traffic isn't going twice as fast. You just have the backup there. So it goes into a blocking state, it's called. And how does spanning tree do this? Well, it uses something called the bridge protocol data unit to spread. So when all the switches come up, they're all equal, and then they're going to determine who gets to be the main switch, and then they'll send up bridge protocol data units, and the lowest number will be determined to be the root switch, and then the others, and we'll talk about how that works, will determine which ports to shut down. So in the end, here's an example. Switch 2 here has F02 put in a blocking state so that flooding doesn't happen. Now, at this point, the PC will send its updating. It'll go to switch 2. Then it will get flooded out and go to, of course, these PCs down here, and switch 1, and then switch 1 will flood it out here. Now, the difference is, and this one will send it down, but you see it's a blocked port here. It's not up and running, so the update does not come back to switch 2. So it blocks the loop. All right. And remember, these switches send out updates on every port except the one which they received it. With with that being built in, the loop won't go round and round anymore. Okay. So that is how they receive it, and this switch over here will say, oh, I can get to the PC back this way and down. And that's just how it will be. Now, should this link go down over here, then the F02 is ready and up and will go and will fail over to it very, very quickly. So, S2 drops the frame because it was on a block port. I think we already discussed that. Now, the names that spanning tree has, and you might need to read a couple of sections a couple of times here. It took me a few years to get spanning tree down to where I enjoyed hearing about it. But we're going to have terms like root port, designated port, non-designated port. So the root bridge is probably the first. Oops, sorry. Let me back that up. Root bridge is probably the first term we need to talk about. Root bridge right here. This is determined because it has the lowest either MAC address or MAC address and combination of other extended IDs. Remember, it's the lowest ID that wins the root war, and all the ports on a root bridge are designated ports. Designated meaning that traffic will flow in and out of them. Okay. Now, what else is going to happen? Let me get a different color here just in case. So we have the designated port, and then every switch that it comes to, they send their information and the type of links that they have, and then the spanning tree will run a calculation of the quality of those links and which link should be shut down. In this case, 02 over on S3 is determined to be a non-designated port. So the designated port and the port for S3 is a root port. Now, the port for S2, 01 is the root port because it's the closest one to the root bridge. Okay? And F2 is also a designated port because it would forward traffic. However, at the other end of it, it can't do it. Based on the calculations, the root bridge told switch 3, hey, put FA02 in an inactive, blocking state, block the traffic from there, so there won't be any loops. But if the link between 2 and 1 goes down, then F02 on switch 3 would come up and run. So you have designated ports, root ports, and non-designated ports. It gets a bit confusing, I know, but it all comes from the root bridge. All right, the root bridge helps determine that. Now, spanning tree algorithm and path cost. I said that spanning tree determines a way to make these costs. And you see on the chart over here on the left, the chart has, this one here is what I'm talking about. It links the cost assigned for each bit of bandwidth. So a 1 gigabit port has a new cost, the revised IEEE cost of 4, and a path cost of 10 gigabits would be 2, 100 megabits would be 19, and I think that that's supposed to be 10 megabits, and this top one here, I think that should be 10 megabits, has a cost of 2, because that's not very much. And this is how the root bridge rates the links between the switches, and then assigns value, and then determines which port should go down. So in theory, the slowest ports are in the blocking state. All right. The steps for all of this are on 2125. Pay attention to it when you get to that point in the curriculum. Now, this is what I put this in just because you know I love Wireshark, and I'm hoping you're loving to love Wireshark as well. When you capture some traffic and you're in a network with spanning tree, you can see the spanning tree protocol and take a look at the BPDU types, and then you can see what the bridge identifier is, port identifier, hello times, etc. So remember your friend Wireshark. Whenever you learn about a new protocol, go and see if you can generate some traffic on it. Okay? Now the last slide for this section was talking about system ID, and that is how we determine who the root bridge is going to be. Now, if you take all of your switches out of the box and just say, okay, pick a root bridge, the root bridge will be the one with the lowest MAC address. Now, in the old days, pre-VLAN days, first of all, the cable bandwidths weren't that fast, and there weren't very many VLANs. So spanning tree ran on a slightly less complex scale. But since the bandwidths have improved, you notice that box I made where the path cost for bandwidth got updated. And also VLANs now have a piece of that BPDU message, in that they extend for the VLAN number, adds to it to separate it out, because you can run different instances of spanning tree per VLAN, which is very complex. All right, and that's in 2129, and that finishes up the first part of this. I hope you enjoy it and get into the studies here, and I'll come back with parts 2 and 3 in just a bit. Thanks.